In the next subsection, I want to look at the LCP array. And that will be a way to augment the suffix array with something that gives us more power, gives us more ways to work with the text that the suffix array is built from. And my motivating question was, which feature from suffix trees did we actually use in some of the more advanced applications of suffix trees? And in particular, the one of this longest repeated substring. So remember, longest repeated substring is you've given a text and you try to find two positions where when you start reading from there, you see the same string, and you would like to know what's the longest you can keep going and read the same text. What's the longest string you find twice in the text? So let's switch to that one. Since you had time before to vote, let me just show this right away. And most of you got this. It is the string depth of the internal nodes. And the reason was, again, here we have the famous suffix tree, for example, that I bored you with for 2 weeks now. If we compute the string depths of the nodes, so that's just the length of the string on the path from the root to that. Okay, sorry, you didn't see that. So here's the answer. C is the right one. And so here's y again, just as a reminder. We annotate each node with the length of the string from the root that leads to this node. That is the string depth of that internal node. And then the longest repeated substring was the path label to a node that has the largest string depth. So the largest string depth was 3 in the example, and we had Anna and Ben as 2 examples. Here, let's simplify the task a bit and not ask what is the repeated string, but just how long it is. And then literally just the string depth is the answer. And in this case, it was easy then to find that. But let's for now focus on just having the string depth of all these internal nodes. The suffix array doesn't give us that. The suffix array just gives us, maybe in gray. So here's the suffix array. It's a bit weird to draw this as an array, but you know, in a sense, it is just that. Needs some artistic talent that I'm lacking. So if you imagine to pull these down to the same level, then they form an array, and that's the suffix array. It just doesn't give you the blue numbers. So the idea is, if it doesn't yet give us the blue numbers, let's store the blue numbers on top. But we have to find a way that we can link this together with the suffix array, because we don't have the tree, we don't have the shape and the topology of the tree anymore. We wanted to get rid of that. So what we'll do is the following. We have the leaves connected left to right in the suffix array. From each of these connecting lines, we can make a detour through the lowest common ancestor of those 2 nodes, of those 2 leaves. Okay. Some go all the way back up to the root. You can have this several times for some of the nodes. That's a big mess, I guess. Maybe instead of drawing it like this, I don't know where that text came from. So that's the concept, but let me just draw it as a single line. So between these 2, we jump back to the root. Between these 2, the lowest common ancestor of 5 and 7 is this one. Then here we go to this, here we go to this. Between those, we go back to the root, this, back to the root, this, and this. Okay, I think that's a little clearer. And so the LCP array, as formally defined on the slides, is just the string depth of the nodes that you point to here. So it's 0, 1, 2, 3, 0. This one's a 3. This one's a 0, a 1, and a 2. Okay. In other words, the LCP array starts is always between two suffixes. So the indexing is a bit inconvenient. It doesn't help to call it index 0.1. So instead we start at 1. And the rth entry, say r equals 1 would be this one, means we take the longest common prefix of the suffixes that start at the position and the previous one. And if you look at the suffixes here, this one starts with is just the $, and this one is $. They don't share any common letters at the beginning. They have a longest common prefix of length 0. That's why the LCP array entry here is 0. Okay. So same way as the suffix array is reading the leaves from left to right, the LCP array is reading the string depths between adjacent leaves from left to right. And if you just want to find the maximal string depth that ever occurred in the suffix tree, then you can just find the maximum in the LCP array. That part's really easy. And let's look at this a bit more. And that's a beautiful connection. So I definitely want to show this in some detail. This is the suffix array for our famous example. You may remember these numbers by heart now. There they are. These are the suffixes in sorted order. What you see in red between the two adjacent suffixes is the longest common prefix. So these two have just the letter A in common, and then they differ at the second letter. These two both start with Anna, but then they differ, and so on and so forth. And for some strings, it's no common prefix. Okay? So that's why the LCP array for this example is 0, 1, 2, 3. That's just the length of the red strings. And that's the same numbers that I've shown you before. So 0, 1, 2, 3, 0. If you go back to that slide, it's 0, 1, 2, 3, 0. Although that 0 looks like a 6, it's a 0. All right, so far nothing new. Now, if you don't just look at adjacent suffixes, but a whole range, say from here to here, all these 4 suffixes start with an A. So in a sense, there's a plateau where they all share an A as a common prefix. At least an A. They may share more if, in this case, you go further, make the interval slightly smaller. And you can draw this for the other ones. Now, so these are called LCP intervals, but we don't really store them. That's just something we envision, or something in our mind for now. The cool thing about these is that if you now compare them with the suffix tree, there's a one-to-one correspondence between the LCP intervals and the internal nodes. And that's shown here. So let's pick an example. Let's pick this AAA, which corresponded to this interval. These 4 suffixes all start with an A. And so what this correspondence means, there's a range where all suffixes start with an A, and that range corresponds to this internal node. That groups the same 4 suffixes together, and their shared prefix is the path from the root to that node. And that's not coincidental. This is always true. Whenever you have an internal node in the suffix tree, for example here this ban, leads to that node, there is a corresponding LCP interval, so a range in the LCP array that is at least a certain value. Notice that the LCP array in this example, where we had A as the shared common prefix, all the numbers in between are at least 1. You never go down to 0. For this one, the interval is short. It's just these 2, and 3 never goes below 3. Well, that's kind of an empty statement. What this slide is supposed to convince you of is if you have the suffix array and the LCP array, basically all information that used to be in the suffix tree is already represented. It's a little contrived, and you have to think around corners to get there, but it's all there. It's nothing really lost by just looking at these 2 arrays. You can, from these 2 arrays, figure out what the suffix tree is. Okay, and we'll explore that a bit at the end. So that's this statement. Those 2 arrays really give you everything that is needed for the tree.